So this is for number 23. You have two parallel non-conducting rings with their central axes along a common line. Ring 1 has a uniform charge Q1 and a radius r. Ring 2 has a uniform charge of Q2 and the same radius r. The rings are separated by a distance of 3r. And if you look here, the question is, and you'll notice ring 1 is a distance r away from P, which means the other one's 2r away from P. The net electric field at point P on the common line, a distance r from ring 1, is 0. And the question is, what's the ratio of the charges? Well, if you remember from your notes or from the reading, here's the equation for the electric field along the axis of a ring of charge, where z is the distance away from the center along that axis, and r is the radius of that ring. So what do we have in this case? I just want to point out one little quick note on this one. 2 pi r times lambda is actually the total charge on the ring. It's the circumference times lambda, which is the charge per unit length. So that you can just write as q. And that makes this problem a little bit easier. If we know the electric field is 0 at this point, we know the electric field due to the first ring pointing this way has to be equal and opposite to the electric field from the other ring pointing this way, assuming that they're both positively charged. I'm not told that, but I'm just going to make it positive. It would be the same if they were both negatively charged. So what must be true? These two electric fields, electric field due to ring 1, must be exactly equal to the electric field due to ring 2 in magnitude, but of course opposite direction. Plugging in our numbers, the first ring we know is a distance r away from the center, so we're plugging in r here, both for this and of course for the z down here at the bottom. And the second one, therefore, by deduction, has to be a distance of 2r away from this side. And so we're going to plug that in for z on the other side. And we do that, notice here in red, Q1 and Q2, the total charge on the rings, we know has to be different. Solving that, over here you only put 2r squared raised to the 3/2 power. Well, r squared, that part's easy. To the 1/2 becomes r cubed, just becomes r cubed. The 2, however, we're stuck with a rather strange radical. So the r cubed comes out. We end up with 2 to the 3/2 power. Over here we end up with 5r squared to the 3/2 power. R comes out, becomes r cubed, but we still end up with 5 to the 3/2 power. Rearranging a little, or first of all, canceling some common terms, we can get rid of all of this on both sides. And we can get rid of an r on both sides, which is kind of nice. Leaving us just with this expression. Finally, we're looking for the ratio of Q1 to Q2. So rearranging this to find that ratio, we get Q1 over Q2 is equal to 2 times 2 to the 3/2 power over 5 to the 3/2 power. Stick it in your calculator. You can give a numeric approximation. You could actually leave it in this form. You could actually write it as 2/5 to the 3/2 power, or you could do some creative things, but basically it becomes out roughly 0.506. In other words, the charge on Q1 is roughly half the charge that it is on Q2. Hopefully this helps.